In this video, we'll be looking at the second part of third problem of UPSC 2024 Civil Services Mains Statistics Optional Paper 1. So it has two parts. First part is write the importance of Cramer-Rao inequality and Rao-Blackwell theorem. And second thing is if x follows Bernoulli 1 comma theta, so then find the binomial 1 comma theta, then find the uniformly minimum variance unbiased estimator of theta comma theta into 1 minus theta. So first of all, if we consider the Cramer-Rao inequality, so Cramer-Rao inequality, so first thing is like it provides the lower bound. So the lower bound for variance of any unbiased estimator, under the regularity condition. So we are having variance of theta hat is greater than or equal to 1 by n into I of theta, where I of theta is the information for IID sample of size m. And the second thing is, so any unbiased estimator attaining this Cramer-Rao lower bound is called efficient, and so that is optimal in the class of unbiased estimators. So the second thing that we can write about the importance is it serves as an benchmark of efficiency. And third thing is, so if we are having like so third thing is it helps us to assess the quality of estimators, because like we can compare with the competing estimators and show how this information affects the precision. And it is also used to derive our asymptotic variance of MLEs, and it also helps us to study asymptotic efficiency. So we can cover like these four major points in Cramer-Rao inequality. And in Rao-Blackwell theorem, so in Rao-Blackwell theorem, like first, like if we condition an unbiased estimator on a sufficient statistic, it never increases the variance. So that means like if suppose t is sufficient and theta hat is unbiased, so then this theta tilde, which is expectation of theta hat given this t, so this is unbiased, and this variance of this estimator would be always less than or equal to variance of theta hat. So that means this gives us like more constructive method to improve any unbiased estimator. So second thing that we can talk about this Rao-Blackwell theorem is if we combine with the completeness, it gives us a UMVUE. Like for example, if t is complete and sufficient, so then expectation of E hat given t, expectation of theta hat given t is unique UMVUE. So therefore, completing with this completeness will give us like UMVUE. So that is what this Lerman-Scheffer theorem as well. And the third thing is, so first thing is about giving a good method. Second thing is about like combining with completeness to give a UMVUE. And more third one, like we can also just write a bit about it provides a systematic way to obtain the best unbiased estimators. So yeah, so any like 3-4 points on these will be valid. Now for the second part, like we need to find the UMVUE of binomial 1 comma theta. So basically that means it's Bernoulli. So if you are having, so basically we need to find UMVUE of theta into 1 minus theta for x1, x2 and so on xn following IID Bernoulli theta. So if we consider xi, so xi can take only 0 or 1, and probability of xi is equals to 1 is theta. So first, like if we find the joint PMF on sample only through this summation I is equals to 1 to an xi, So we can see it's a binomial n comma theta. Like for example, t is, suppose if I consider summation I is equals to 1 to n xi. So this follows binomial n comma theta. So, and moreover this binomial family is complete. So t is sufficient for theta. We know that t is sufficient for theta, and this binomial family, binomial family is a complete family. So therefore t is also complete. So that means t is complete and sufficient. So we need to find an unbiased estimator expressed as a function of t. So if I consider u as some t into n minus t by n into n minus 1. So if I consider expectation of u, so expectation of u would be, or like if I find the expectation of t into n minus t, so that's nothing but n into expectation of t minus expectation of t square. We know expectation of t is nothing but n theta, so this is n square theta, minus expectation of t square is variance of t plus expectation of t whole square. So that's nothing but n square theta minus n theta into 1 minus theta plus n square theta square. So that is nothing but n square theta minus n theta plus n theta square minus n square theta square. So that is nothing but, so n minus 1 we can clearly see it is common. So n if I take common, so n theta if I take common, so that is n minus 1 plus here n theta square if I take common, or minus n theta square if I take common, this is n minus 1. So that is nothing but n into, so n theta into 1 minus theta into n minus 1. So that is expectation of t n minus t. So that means this expectation of t into n minus t by n into n minus 1 is theta into 1 minus theta. So that means this u is an unbiased estimator of theta into 1 minus theta. Now we can clearly see u is a function of a complete and sufficient statistic t, and it is also unbiased. So therefore we can use the Lehmann-Scheffé theorem. So from Lehmann-Scheffé theorem we can say u is unique UMVUE of theta into 1 minus theta. So alternatively, like we can also express the same in the other form, like theta into 1 minus theta. So basically our conclusion is, so that is t into n minus t by n into n minus 1. So I can also write the same as, so if I give this t to this, so t by n, and if I multiply with the one more t, so if I multiply and divide by t, see that this is nt minus n by t by n square into n minus 1. So, or if I divide by t, so if I divide by the t, this is t by n into n, if I take common, this is 1 minus t by n into n minus 1, that is n into n by n minus 1 into x bar into 1 minus x bar. So this is alternatively we can also write the same UMVU in this form. So therefore the UMVUE of theta into 1 minus theta is summation xi into n minus summation xi by n into n minus 1. So that's it for this video. We'll meet in the next video.